In progress.
8051 timer, bar counter, hardware, delay, programming. So the timer and counter programming for 8051 will be mainly the hardware delay programming. So we already discussed that there is software delay and hardware delay. Software delay means the delay that we generated using loops. With loops, we can create software delay. Hardware delay is the delay that is produced by using the timers. So one of the main advantages of using this hardware delay is that here the timer is generating the delay. At that time, the processor is free to do other operation. But in the case of software delay, the processor itself running the loop and creating the delay. That means the processor is busy at that time. But in hardware delay, a timer is used to generate the delay and the processor will be free to do some other operations. 8051 has two 16-bit timers, that is timer 0 and timer 1 that we discussed when we study about the timer. So here it is the programming of timer. So first a simple program, that is write a program to generate 20 microsecond using a delay of 20 microsecond using internal timer 0 of 8051. After the delay, send a 1 through port 3.1. Assume the suitable crystal frequency. So 8051, when it is works in a timer mode, it uses the internal clock. So 8051 microcontroller is connected with an oscillator, and the oscillator is having some frequency. Here we select the crystal frequency as 12 megahertz, and the timer frequency will be f oscillator by 12. So you will get 1 megahertz timer frequency. Hence, each count will require 1 by 1 megahertz. So this is the frequency. We need the time. The time is calculated by 1 by f, that is 1 by 1 megahertz. You will get 1 microsecond. The count, time of one count. Thus, for 20 microseconds, the desired count will be 20. So 20, it is in decimal. We need to convert it into hexadecimal. 20 in decimal is 14 in hex. So for an up counter in mode 1, so usually the delay programs are generated by using the timer mode 1. Timer 1 or timer 0, any timer can be used, but it will be operated in mode 1. We already discussed the different modes of timers, and mode 1 is a 16-bit timer mode. The maximum count, the count can be calculated by using the equation, that is count is equal to maximum count minus desired count plus 1. Because here we are up, it is up counter. So if you need to get a count 20 counts, it will for the 20 microseconds. If you do up counting, you need to give the value. If you give the 14 hex load to the timer, so it will start, the counting starts from that value till it gets overflow. So we will get an indication when it gets overflow, that is FFFF. So when if we load the value 14, it will count from 14 hex to FFFF. So you need to load the value. If it is since it is up counter, you need to subtract the value from the maximum count. So maximum count is FFFF minus 14. Here we add a plus 1 because and we reach FFF, then in the next count only it gets overflow. When it rolls over FFF to 00, only the overflow flag will be set. So we are adding plus 1, that is to another one more pulse only it will get overflow. So we are adding plus 1 to get the exact count. So the value FFFF minus 14 plus 1 will get FFEC hex. So this is the count that should be loaded to the timer register. So to do a timer, this function, some of the instructions should be given. That will be same for any delay programs. Only difference is that the value that you load to the timer register. നമ്മൾ ഈ ടൈമർ രജിസ്റ്ററിലോട്ട് ലോഡ് ചെയ്യുന്ന വാല്യൂവിൽ മാത്രമേ ഡിഫറൻസ് വരുന്നുള്ളൂ. ബാക്കി ഈ ഇൻസ്ട്രക്ഷൻസ് ഇതുപോലെ തന്നെ നമ്മൾ എല്ലാ ഡിലേ പ്രോഗ്രാംസിലും സെറ്റ് ചെയ്യേണ്ട കാര്യങ്ങളാണ്. അതായത് നമ്മൾ ടൈമറിനെ ഒന്ന് സെറ്റ് ചെയ്യണം. So here it is said that to use the timer 0. So നമ്മൾ ടൈമറിന്റെ ടൈമർ രജിസ്റ്റേഴ്സ് പഠിച്ചായിരുന്നു. This is the timer mode register. Timer mode register is not bit addressable, byte addressable register ആണ്. അപ്പൊ നമുക്ക് ടൈമർ zero and it should operate in mode 1. So timer 0, this part is for lower 4 bits is for timer 0 and higher 4 bits is for timer 1. Timer 0 it should operate in mode 1 ആണെന്നുണ്ടെങ്കിൽ the mode bits should be 0 and 1. So it is in timer mode. Timer mode varnengil C bar T should be 0 to set it in the timer set as a timer mode, and that means we are giving internal clock f isolated by 12 and the clock frequency nammaloda kodukunnathu. So it should be operate in timer mode. So this also should be 0, this is 0 and this is 1. And gate is to enable the hardware control. Hardware control nammal oru switch vechittu namukku timer ne operate cheyanadundengil that is using hardware control using interrupt pins INT0 അല്ലെങ്കിൽ INT1 use ചെയ്യും. ടൈമർ 0ക്ക് INT0 യൂസ് ചെയ്യും, ടൈമർ 1 ആണെങ്കിൽ INT1 യൂസ് ചെയ്യും. സോ ഇത് ഹാർഡ്വെയർ കൺട്രോൾ നമുക്ക് ആവശ്യമില്ല. So this gate is set as 0. So the lower 4 bits will be 0, 0, 0, 1 and higher bits are 0 because we are using timer 1 only, timer 0 only. So we need to set the T mode register. In T mode register #01. That means we are setting, we are using the timer 0. That is only the lower 4 bits is the matter. So to set the mode bits, last 2 pins are used. That is to work in timer mode 0, 01. And here it is timer mode, it is 0 and gate is not enabled, that is 0. And upper 4 bits, that is for timer 1 that we are not using. So all the bits are 0. So we are loading 0, 1 to the timer mode register that will set the timer 0 in mode 1. And next we need to load the value, the count value to the timer register. That is for timer 0, we have a 16-bit register. That is it is separated into 2 8-bit registers. So that is TL0 and TH0. So you know that it is divided into 2 registers. That is timer high 0 and timer low 0, TL0. So you need to load the values to this register. So what is the desired count? You need to load this. Here the desired count is FFEC. So we are loading EC to timer 0, EC to timer 0 and FF to timer low. Timer high we are setting FF and to timer low we are setting EC. So you get the count FFEC. So from this it counts till it gets overflows. So here the value is loaded to the timer register, timer 0 register, that is to timer 0 high and timer 0 low. And move TCON #10 hex, that is TCON register. You need to start the timer. TCON register also we discussed earlier. Let me show the TCON register. So this is the TCON register. So the lower 4 bits of TCON register is for interrupt and higher 4 bits is for timer. For timer, we have TF1 and TR1 for timer 1 and TF0 and TR0 for timer 0. So here this is timer overflow bit and this is timer run bit. So to start the timer, the run bit should be 1, and to stop the timer, the run bit should be 0. So to start the timer, we will give this one timer. To start timer 0, this bit should be set to 1, and to stop the timer 0, this bit will be set to 0. If it in the case of timer 1, we use this bit, TR1 bit, and TF0 is the overflow bit. Overflow bit means when an overflow occurs, this bit is set to 1. So when it overflow means that the timer 0 up counts, and when it reaches FFF, and again, and the next count, the time FFF will rolls over to 0, 0. Then an overflow flag also will be set. So to run the timer 0, the value will be 0, 0, 0, 1, and this interrupt bits all we are set to 0. So the value will be 1, 0, 0, 0, 1, it is 1, and 0, 0, 0, it is 0. That is 1, 0 is the value that should be loaded to the timer TCON register, timer control register. So TCON, that will start the timer 0. And when the timer 0 starts, we are waiting for the overflow flag to set. The overflow flag of timer 0 was TCON 0.5. So here you see this is TCON register, and TCON register, it is 0, TCON.0, TCON.1, TCON.2, TCON.3, TCON.4, and TCON.5. So we are checking this value, that is whether this TF0 is a bit. A bit means it is 1. If it is not bit, means it's a 0. So we are checking whether it is 1 or not, whether an overflow occurs. When an overflow occurs, this bit will be set. And this TCON register is bit addressable register. So you can individually access each bit of this register. So we are checking alone this TF0 bit. TF0 bit alone is checking by using the jump instruction, that is JNB TCON 0.5. JNB we are checking, waiting for the overflow, and when an overflow occurs, till this jump, if not bit, it is given JNB. So when it is 0, it jumps to bit. So this loop executes till TCON 0.5 is a bit, that is if it is set, till it sets. So when an overflow occurs, TCON 0.5 is set, then it goes to the next instruction. Till the overflow occurs, the TCON 0.5 is 0. So it this loop, this instruction is executed till TCON 5 is set. So when it is set, it goes to the next step, that is set B P3.1. This is to send 1 through port 3.1. So set B means the port 3.1 is set. Let's just send a 1 through port 3.1. Then move TCON, hash 00. So TCON, hash 00 means we are clearing the TCON 0.5. TCON 0.5 is now set, and also we start the timer by TCON 0.4 is also set. So by clearing it, we are stopping the timer 0 and also clearing the overflow flag of timer 0. Then we end the program. So this is the program to generate a delay of 20 microseconds. The delay is calculated by using this formulas, and the value, the count is calculated. This count is now loaded to the timer register, and the timer starts counting till it gets overflow. So we are checking whether the timer gets overflow or not, and when it gets overflow, that is the required delay is obtained, then we will do the required action. So here we need to send a 1 through P3.1. So we are setting P3.1 and stops the timer. So next program to generate a square wave of 1 kilohertz from the transmit pin of 8051 using timer 1. The transmit pin is P3.1. And here it is said that assume the clock frequency is 12 megahertz. And this is the most important question. Usually the timer, they will ask to generate a square wave or to generate a rectangular wave, etc. So to generate a square wave means means we have a high, this is what we do for here as a square wave. So this is a square wave, and this should be generated by using the timer, delay in the timer. So here it is said that you have to generate a square wave of 1 kilohertz. So here it is given 1 kilohertz. So 1 kilohertz square wave should be generated. So the total frequency, square wave means it has an on state and off state. Both should be of equal delay or equal time period. So you need, if it is 1 kilohertz, it will be 0.5 kilohertz, and here also it should be 0.5 kilohertz. So 1 kilohertz means the time period will be 1 kilohertz means the time period will be 1 millisecond. So you need total 1 millisecond is the time period. So the on state should be of 0.5 milliseconds. So here it is 0.5 millisecond. The on state is 0.5 millisecond and the off state is also 0.5 millisecond. So we need to generate a delay in which it's a delay of 0.5 millisecond, and the signal should be high for 0.5 millisecond and it is off for 0.5 millisecond. So you will get a square wave. So to generate a square wave, it is just sending a 1 and then 0, but there should be a delay so that only you can view the signal properly. So the delay should be called after sending 1, a delay is called, and then send 0, then a delay is called. So you will get a square wave. So if both the delay on state and off state delay is same, you will get a square wave. If the delays are different, that is a shorter delay for on state and a large delay for greater delay for off state, you will get a rectangular wave. And if you are giving a delay for off state and without not a delay for on state, you will get spikes. So for a square wave of 1 kilohertz, the delay required is 0.5 millisecond. We know that each count required 1 by 1 megahertz. So which is equal to 1 microsecond. Just for 500 microseconds, 0.5 millisecond means it is 500 microsecond. The desired count will be 500. So one count is 1 microsecond. So 500 microseconds means 500 counts. So this is in decimal, you need to convert to hex, or else you can take the maximum count in decimal itself, that is 65,536. That count you can take and minus 500 from that, and then the final value is converted to hexadecimal. Or you can convert the number of count to hex first, and then you can subtract it from FFFF. രണ്ട് രീതിയിലും ചെയ്യാം. ഒന്നെങ്കിൽ നമുക്ക് FFFന്റെ decimal value നിന്ന് 500 minus ചെയ്യുക plus 1 add ചെയ്യുക, and ആ കിട്ടുന്ന റിസൾട്ടിനെ you can convert to hex. That is one method. And another method, that is first the number of counts calculate here, convert the count to hexadecimal and subtract it from FFFF. Hex in the subtract here. So you can't subtract 500 from FFFF because 500 is decimal and FFFF is hex. So both should be in same count. So if it is decimal or if it is hex, both should be in same number form. So the desired count will be 0, 1, F4. For an up counter in mode 1, count is equal to maximum count minus desired count plus 1, FFF minus 0, 1, F4 plus 1, FE0C hex. You will get the count FE0C hex. So here it is the transmit line TXT pin, it is set is P3.1. So it is cleared initially. So it will clear it and move T mode 10 hex. So this here we use the timer 1. So first 4 bit of T mode is for timer 1 and last 4 bits, the lower byte will be for timer 0. So here we use timer 1. So the timer 1 in mode 1. So you can see 0, 1 here will set mode 1 and this is for timer 1. So timer 1, mode 1 is selected. And we load the count FE0C hex to the timer 1 register, that is high FE, and to low 0C. So here we add a 0 to show that it is the hexadecimal value. When it comes here, it comes the alphabets, we add a 0 here. Next is TCON, move TCON #40 to start the timer 1. So here this is the TR1 bit. So TR1 bit is set and all other bits are 0. So it starts the timer 1. And we are checking for the overflow flag of timer 1, that is the 7th bit, the 8th here, this bit, whether it is 1, we are waiting, that is, we are waiting for the delay. So when it is 1, we goes to the next bit, that is P3.1, complement P3.1. So if it is CPL is complement, if it is initially 0, it will now change to 1. And in the next iteration, when it comes, it changes to 0. So this CPL P3.1, that it will toggle the transmit pin after the delay. And then now we are stopping the timer and we repeat the same thing. So again, the when it is high, now it is complemented and now it is high. And again, we are loading the same delay of 0.5 millisecond to the timer. Again, start the timer, wait for the delay, and then it complements. So complements means when it is, if it is high, it changes to low. And this will be repeated and you will get a square wave of 1 kilohertz delay. So next is to generate a rectangular wave of 1 kilohertz having 25% duty cycle from TXT pin of 8051 using timer 1. Here the crystal frequency is also given 12 megahertz. So for a rectangular wave for 1 kilohertz, we are having 25% duty cycle. That is on state is 25 microsecond. Total we have 1 millisecond. Total the time period is 1 millisecond. On that 250 microsecond for on state and 750 microsecond for off state. Here we taken 500 microseconds each for on and off. So it has 50% duty cycle. 25% duty cycle means you have only 25% of on state. In the total time period, we have only 25% of the on state and 75% of off state. So the wave will be like this. That's 25% duty cycle, that is only 250 microseconds or 0.25 millisecond on state and 0.75 millisecond off state. So here we need to find the count each for the on state and off state For on state, it is the number of counts is FA, and you need to subtract from the maximum count minus FA plus 1. You will get the value, some value here, FF06. And the desired count for off state is 750 counts in decimal. So in hexadecimal, it is 02EE. So subtracting it, calculating it, you will get the value FD12. So now write the program. So we need to, it is asked to set in timer 1. So we set the timer 1 in mode 1 and load the value. First we load the value for the on state, that is 06FF. So 06FF is set and the P3.1 is 1. So that you will get a 1 here and waits for the, and start the timer. Starts timer 1 and wait for the delay. And after the delay, the P3.1 is clear. That is, it is P3.1 is now 0. It is clear. And then set the, and now we stop the timer. And now we load the value for the off state. Off state, the value FD12. So 122 timer 1 low and FD2 timer 1 high. And again, we start the timer and we check for the overflow flag. So after that delay, again, the timer is stopped and we repeat it. So we add the delay value for the on state. Then the 3.1 is set, that is high here, and wait for the delay. Then after the delay, the timer is stopped and the new value, the P3, it is clear or P3.1 is clear, and it waits for and loads the new value, that is for the off state, and then start the timer. So this is repeated, you will get a rectangular waveform. So now, if the system frequency is 12 megahertz, it is clear that one count requires 1 millisecond. So in mode 1, we have 16-bit counter, 16-bit count, that is from 00 to FFF is the maximum count. Hence the maximum pulse, that is 2 raised to 16. 2 raised to 16, that is 65,536. We can calculate in this way also, that is my maximum count is minus the maximum count minus the desired count plus 1. So you will get the 0. So when you load 0, it will have rollover back to 00 to overflow. So it starts from 00 to it. When it comes FFF, then rolls in the next count, it rolls over back to 000, then and the overflow flag also will be set. So hence maximum crystal frequency, maximum delay, if crystal frequency is 12, it is 65,536. That is the maximum microsecond, is that is maximum delay, that is 65.536 millisecond. Similarly, if the crystal frequency is 11.0592 megahertz, that is the crystal frequency usually we get for an 8051 microcontroller. So this is the actual crystal frequency of 8051 microcontroller, that is 11.0592. That is 71,106 microseconds. And you will get 71.106 millisecond delay. So this is the maximum delay that can be generated using the timer, this timer. But the next question, that is write a program to generate a 1 second delay using timer 1. So we here the maximum delay, we said that by using a 16-bit count, you will get maximum delay of 71.106 millisecond or 65.536 millisecond. But here it is asked to generate a 1 second delay. So the maximum delay, it is 65.536 millisecond. Hence, to get a delay of 1 second, we will have to perform it continuously. we have to perform the continuing repeated in a loop, counting repeated in a loop. So in a loop, we need to repeat it to get a 1 second delay. So let's keep the desired count as 50,000, that is 50 millisecond delay. So this is the desired count. So when you get as 50 millisecond delay, if you repeat it for 20 times, if the loop is executed 20 times, you will get a 1 second delay. So now 50,000 is equal to C350 hex. So maximum count is FFF minus C350 plus 1. You will get 3CB0 as the count value. So you need to repeat this 20 times. You will get, this will generate a 50 millisecond delay. So repeating this loop for 20 times, you will get 1 second delay. So in mode 1, so we set the timer in mode 1, timer 1 in mode 1, and load a value that is 14. 14 is the hex of 20. You need to repeat the loop for 20 times. So you the loop count in R0 register and load the value of the count, that is B0 to lower, timer 1 lower, and 3C to timer 1 higher, and start the timer, repeat the loop. So once this loop is executed, you will get a 50 milli. So when it rolls over, when the overflow occurs, it stops the timer, and DJ, by using DJNZ, we repeats the loop. 0, repeat. So this loop executes 20 times, and you will get a total of 1 second delay. So next, write a program to read the data from port 1 10 times, each after 1 second delay, and store the data from RAM location 20 hex onwards when the operation is complete. Ring an alarm connected to port 3.1. Assume the clock, which is equal to 12 megahertz. So you already know the program to write to generate a 1 second delay. So here you need to read the port 10 times after a 1 second delay. Port 1 10 times after a 1 second delay. And read the port, and you need to store the data in 20 hex onwards. So when you read each time the port, the data should be stored to 20 hex memory location, from 20 hex onwards to continuous 10 location. After completing the operation, you need to ring an alarm that is connected to port 3.1. So you need to set the port 3.1, which will ring an alarm. So as seen from the previous program, for a delay of 1 second, we have count is equal to 3CB0 hex. So counting has to be performed 20 times to get, when you load this, you will get a 50 millisecond delay. 20 times when you repeat, you will get 1 second delay. Also note that all the ports of 8051 are output ports by default. So to read from port 1, you need to set it as an input port. So to program a port as input port, all ones must be sent through it. So first you clear P3.1 where you are connecting the alarm. So first initially it is cleared, and move tmode comma #10 hex, that is tmode in timer 1 mode 1 for, and move 90 hex #0FF, that is the 90 is the address of port 1. Port 1 is to declare it as input port. We sent all ones to port 1. So you need to declare it as an input port. Next, you need to repeat the loop for 10 times. You need to read the port 10 times. So a loop count is given to R0 register, and R1 register is used for 20, that is 20 times you need to repeat the delay program to get a delay of 1 second. And move at the rate R1, 90, that read data from port 1. So once you read data, here you have 20 hex. This 20 hex means from 20 hex location, you need to store the data. So R1 is equal to 20 hex means you have this value. It is to store the data from 20 hex memory location. So first you read the port and increment R1, and you call the delay. That means